In this example, we want to write a chemical equation that represents the combustion of butane. Now, the chemical formula of butane was given to you, C4H10. All right, what's combustion? Combustion is adding oxygen and making carbon dioxide and water. So let's take the butane, C4H10, and add oxygen to it. Now remember, oxygen's a homonuclear diatomic, so oxygen exists as O2. So it's C4H10 plus O2. What does that produce? That produces carbon dioxide, which you know is CO2, and water, which is H2O. So that's the chemical equation of combustion. Unfortunately, it's not balanced, so we're going to have to balance it. Before we do that, however, let's add phase symbols, because we know everything we need to know to determine the phase symbols in this reaction. You don't always know the phase symbols in a chemical reaction. Sometimes they're given. Sometimes you just have to leave them out because you don't know them. But when you know them, it's a good idea to add them. In this case, we know all the phase symbols we need. You see, the problem tells us that butane is evaporated before it's burned. So that means butane is a gas, and we can go ahead and put the gas symbol next to it. We know that oxygen is a gas. After all, we breathe it in. We also know that carbon dioxide is a gas because we exhale it. Now, water is a liquid at room temperature, but when you're burning things, you're not at room temperature. You're at a much higher temperature, and water typically evaporates at those temperatures. So water is a gas here as well. So all of our substances are gases in this particular chemical equation. All right, now we can settle into the real business, which is balancing this chemical equation. Let me rewrite it, and then let's look at balancing the carbons. Currently, there are 4 carbons in the reactant side and only 1 on the product side. The easy way to fix that is simply to multiply carbon dioxide by 4. When we do that, we get 4 carbons on both sides of the equation, so the equation is now balanced. All right, let me rewrite the equation again so we can balance the hydrogens. Remember the trick. The trick is to balance elements that appear only once on each side of the reaction. Carbon appears only once on each side of the reaction, and hydrogen appears only once on each side of the reaction. So those are the elements to start with. I have 10 hydrogen atoms on the reactant side and 2 on the product side. I don't want to mess with C4H10 because I've already used it in balancing the carbons. So the only thing I can play with is H2O. If I multiply H2O by 5, I get 10 hydrogens on the product side, and that matches the 10 hydrogens on the reactant side. There's only one element left to go, and that's oxygen. Now, oxygen's a little annoying because it appears twice on the product side of the reaction, but we can handle that. So let's rewrite the equation. And now let's look at the reactant side. There are 2 oxygen atoms on the reactant side. What about the product side? Well, oxygen appears twice, so we have to deal with it twice. In carbon dioxide, I have a total of 8 oxygen atoms. There are 2 in the molecule, but there are 4 molecules, so a total of 8 oxygens coming from carbon dioxide. There are a total of 5 oxygens coming from water because there is 1 oxygen atom in the water, and we've got 5 water molecules, so 5 times 1 is 5. So we have 8 oxygen atoms coming from carbon dioxide, 5 coming from water, for a total of 13 oxygen atoms. So I've got 13 oxygen atoms on the product side. I need to get 13 oxygen atoms on the reactant side. Now, about the only thing I can do is multiply O2 by something. What do I have to multiply O2 by to get 13 oxygen atoms? Well, the answer is a fraction, 13 halves. If I take 13 halves and multiply by 2, what do I get? 13. So 2 oxygen atoms in each oxygen molecule times 13 halves molecules is 13 oxygen atoms. That's what we need to balance the equation. So now at least the equation is balanced. We have the same number of carbons, the same number of hydrogens, and the same number of oxygens on each side of the equation. So this is another example of a chemical equation that you have to use a fraction in order to balance. Don't worry about using fractions. Go ahead and use them, then just get rid of them in the end. How do we get rid of this fraction, 13 halves? We multiply by 2. If we multiply the product side by 2, 13 halves will become 13, and we'll get rid of the fraction. However, remember the golden rule of algebra. Do unto one side as thou wouldst do unto another. So if I'm going to multiply the reactant side by 2, I've got to multiply the product side by 2 as well. All right, now let's go ahead and do the math. If I multiply the reactant side by 2, C4H10 becomes 2 C4H10. 13 halves O2 becomes 13 O2. Then if I multiply the product side by 2, 4 CO2 becomes 8 CO2, and 5 H2O becomes 10 H2O. Okay, so now the chemical equation is not only balanced, but it also has no fractions in it. So it is a balanced chemical equation that is also physically reasonable. So that's our final answer.